Hi, and welcome to our lecture on wind speed measurements. Right now we're talking about different kinds of wind speed sensors. And in this lecture we're going to talk about wind profilers. There's another video out there, another lecture on the theory behind wind profilers, kind of a general theory. Right now we're going to talk about the different types of wind profilers that are available. And wind profilers can be broken down according to their frequency or wavelength at which they operate. You can see that there's a 50 megahertz, a 400 megahertz, and a 915. Remember, megahertz or the frequency and the wavelength are connected or related by the speed of light, if you remember the equation, basic equation of physics. So that objects that have a really short frequency or small frequency have really long wavelengths, and ones that have really high frequency have really short wavelengths. So we're going to start out with the one that has a really long wavelength or very slow frequency, which is the 50 megahertz wind profiler. So as I said, 50 megahertz is really a slow or short frequency, so you're going to have long wavelengths. So the wavelength behind, or the wavelengths for these wind profilers are typically really large, 6 meters, which is about 18 feet. Believe it or not, that's a really long wavelength. So it's operating in the VHF. Because it operates at higher longer wavelengths, it has less attenuation, meaning that it can travel great distances through the atmosphere. Specifically, great distances between 2 to 16 kilometers. So it can go up through the troposphere and even into the lower stratosphere, believe it or not. It's not uncommon for these types of radars to be measuring winds up at 20 kilometers, which is well into the stratosphere, the middle of the stratosphere. And if you remember, we talked about the wavelength and antenna size. So really big wavelengths require really large antennas. These antennas are on the order of the size of a football field, 100 meters by 100 meters. So we said that these have very low resolution, low attenuation, but they have poor resolution, meaning that the smallest element that they can detect is typically on the order of about 6 meters, which actually is not very good for this particular type of wind measuring device, believe it or not. A more common wind profiler is the 400 megahertz or 74 centimeter wind profiler. As you can see, it has a higher frequency, which means it has a much shorter wavelength. So this is operating in the UHF, the frequency, UHF frequencies. So because it has a shorter wavelength, it also means the attenuation is greater, so it doesn't travel as far from the radar or the wind profiler. So this only measures up to about 9 or 10 kilometers, which is just the upper part of the troposphere, and not quite into the tropopause, above the tropopause. Tropopause is typically somewhere around 11 or 12 kilometers up. However, it doesn't take a large area. It doesn't take up a lot of space, the antenna. The antenna is only 12 meters by 12 meters, which is, about 36 feet by 36 feet. Still, it's kind of large, but not as large as the other one that we talked about, the 50 megahertz. So it's not as big as a football field, but it's not as small as a breadbasket or something like that. Because the wavelengths are shorter, it has much better resolution. They say that it measures winds every 250 meters going up through the atmosphere. As a matter of fact, this wind profiler, the 400 megahertz wind profiler, was the one that was used by the United States. We actually had a wind profiler network across the United States back in the 1990s and into the 2000s, the early 2000s. It was called the NOAA Profiler Network, or NPN. Started in 1992. They put up these wind profilers all across the Midwest. Did not require people to be there to watch these. They just put them out in the field and let them go. And they measured the winds. They gave hourly output for the winds, gave actually a vertical wind profile. They took 6-minute samples of the winds and averaged those into an hour. So every hour, 24 hours a day, 7 days a week, you got the winds from the surface all the way up to about 10 kilometers. So it's almost like having a radiosonde, sending up a radiosonde every hour, except you don't get a temperature profile. All you get are the wind profile. This was shut down for several reasons. One very poor reason that they shut this down was because of money. And these don't really cost a lot to operate. But the other reason this was shut down was because of money. That sounds funny, but these wavelengths, the 400 megahertz band, is right about where cell phones operate. And of course, throughout the early part of this century, cell phones became really popular, so they needed more frequencies to operate these cell phones at. And gosh, guess where they got those frequencies? They shut down the Wind Profiler network, and they sold all of those bands. The government, the FCC, sold those wavelengths to telecommunication companies. But this is the map that shows all of the wind profilers. They focus the Wind Profiler network across the central part of the United States, and the reason for that is during the summertime, it's really nice to look for that low-level jet that feeds thunderstorms. So they use these actually to help predict where thunderstorms were going to be. That's not as important as having a cell phone in your hand, right? This is the output. This is actually from 2000. I used to actually teach this in this class. We'd go through and look at the wind profiler data, and we'd interpret it. We don't do that anymore, but I thought it'd be nice kind of historically to show you what it looked like in case you want to set up your own wind profiler network. God forbid, though, because you'd have to talk to the FCC. And well, I'm not going to get into politics, never mind. So, along the left side, you have height in, I think that is in thousands. No, that is in kilometers. I was going to say that's in... Yep, that's in kilometers. And on the right side, you've got pressure on the right side. You can see actually the data goes all the way up to 17 kilometers, which is pretty good. And then they color code the winds based on the strength of the wind. And the wind speed is in meters per second. Along the bottom, you can see if it's red, that means the wind speeds are more than 50 meters per second. We talked about this to get the wind speed in knots, double meters per second. So everywhere you see in red everything you see in red is more than 100 knots. So basically this is showing you the location and the depth of the jet stream over this particular wind profiler. Along the bottom is the time. Each one of these, as you go up, you can see from left to right the winds, and each one of these is at a particular time. So you can see the time progression. And it looks like on the right side is the oldest, and along the left side is the newest. So it looks like over this particular location, Fairbury, Nebraska, it looks like a jet stream is starting to move in, and actually the jet stream is actually descending. It looks like it's getting a little bit closer to the ground with the strongest winds that are 100 knots at 8 kilometers. And as I mentioned, there's the time hacks there every hour. And then we talked about the wind speed key, and that's in meters per second. So, yep, there's your jet, more than 100 knots, and it's pretty impressive. This was really a great network and provided a lot of information for forecasters. There's the third type of wind profiler. We talked about the 50 megahertz and also the 400 megahertz. Now the 915, that's a much higher frequency, so that means it's much shorter wavelength, only 33 centimeters. So this operates in the UHF, and since it's a shorter wavelength, that means that it's attenuated more easily, so it doesn't go up through the atmosphere that very far. And these are actually used to measure winds in the lowest layers of the atmosphere, typically for boundary layer studies. Boundary layer means the lowest kilometer or two within the closest to the surface of the Earth. These antennas were very small. They're 3 meters by 3 meters. They're about the size of, well, maybe, yeah, about the size of a bed, maybe a king-size bed. But they have very good resolution down to 60-meter gates, so it gives you the wind speeds every 60 meters. And UND, we actually, Department of Atmospheric Sciences, had one that we operated for a number of years out in Mentor, Minnesota. It was called the Glacial Ridge Observing Site. So some of the advantages and disadvantages of wind profilers. The advantages, of course, is they measure winds from the surface all the way up above a point, many kilometers through the atmosphere. It's remote sensing. They do it continuously, although you can average it. And as we saw with the wind profiler network, they gave you an average of winds every hour. And they measure directly above a site. As you know, radiosondes, the balloon goes up and it travels downwind. So by the time you get to the upper atmosphere, you're measuring a site that's about 100 miles away from where you launched it. It can measure, the wind profiler can measure horizontal winds and also vertical wind air velocities. They have a high temporal and spatial resolution, which means that they measure very frequently and also many levels of the atmosphere, very small level increments. The cost per observation is extremely low, much lower than radiosondes, and they can operate unattended all year long. And they don't complain much as compared to weather observers who send up balloons. Disadvantages, of course, they require a large amount of bandwidth in the electromagnetic spectrum. When I first started teaching this class, we were more concerned about television and radio stations encroaching on it. But of course, we've seen that the wind profilers fell to the whims, not the whims, but the needs of our telecommunication via cell phone. So that, in a nutshell, is wind profilers. We'll get into Lidar and Sodar very quickly. Lidar is light detection and ranging. Basically, this is an instrument that has a laser that pulses, and as that light travels through the atmosphere, it's scattered by dust particles and other things in the atmosphere. We can measure that scattering light as it comes back to a receiver. And based using signal processing, we can figure out the Doppler velocities. So it's very similar to a Doppler radar, or even for that matter, a wind profiler, except instead of using UHF or VHF, we're using visible light at particular frequencies. And as I mentioned, this determines the radial velocity of the air. Based upon the Doppler shift coming off of, it bounces off of aerosols. And the LiDARs are used for research, and also they're used, mostly research, I take that back. I was thinking about the NASA. NASA has one on an airplane that they use for wind shear detection, and that is a research platform. Also, you can see there NOAA and the National Center for Atmospheric Research have LiDARs also, in which they do studies. They do research with their LiDARs. And the last type of speed sensor we'll talk about is Sodar, which is similar to LiDAR and radar, except it uses SO, which is sound. So it sends out an acoustic wave through the atmosphere. And the receiver, from where it was transmitted, it receives the signal bouncing off of objects in the atmosphere, measures the Doppler shift actually, and from that it can determine radial velocities also. So it works very same principle as your vertically pointing wind profilers, and also LiDARs in some respect, except they're using sound waves instead of light or electromagnetic radiation. And of course, it's bouncing off of the sound is bouncing off of regularities in the atmosphere, discontinuities, whether they be temperature inversions or temperature profiles or temperature changes. But regardless, it uses more or less the same principle, except it's an acoustical signal. So that is the overview of wind profilers, lidars, and sodars, and I hope you enjoyed it.